Good afternoon, everybody. Welcome to another Oxford Sparks live event, which is part of our Science at Home campaign. If you're new here, then you should know that we're holding these every week during lockdown. So do join us again next week, and there'll be more detail about that at the end of this broadcast. If you are new, then do consider subscribing to our YouTube channel so you can keep up to date with all of the latest animations, videos and live events like this. And also you can follow us on social media. We're on Facebook, Instagram and Twitter at Oxford Sparks, and that's another great way to keep involved and in touch with everything going on science-wise at the University of Oxford. So to crack on with today, I'm very, very pleased to be joined by a computer scientist. I feel we don't often get to talk to computer scientists so often, and it'll be really great to hear what it's like to do a computer science PhD, a little bit about what it all involves. So good afternoon, Maaike Zwart.
Good afternoon. Thank you very much for inviting me. I'm excited to be here. And as you say, I'm a computer scientist. My work, I'm a PhD student. This is my title. It says, on the compositionality of monads via distributive laws, which is quite a mouthful of jargon. So I'm going to try to sort of break that down for you to explain what I'm actually doing.
Absolutely, yeah. We're really looking forward to that. As you say, I think something like this maybe can seem a bit inaccessible, but I've been chatting to you about it and it's such exciting stuff. And I think that we can tell everyone all about it. So maybe you could just spend a couple of minutes in your own words telling us a little bit more about what that means, and then we can go from there. And don't worry, even if you don't know what algebra is, it's fine. We're going to break it down.
Yeah, so let me start explaining all these words that are in my title. That will tell you a lot about my research. The first one is compositionality. That really means how things fit together. It's kind of like Lego blocks. You can build big things out of small bricks, and that is what compositionality studies. It's how small things fit together to make more complicated things. And the small things that I'm studying are monads. And these are structures that are used in functional programming a lot. They're kind of the Lego bricks for functional programming, or at least they're a kind of color of Lego bricks for functional programming. But they're really hard to understand and really hard to explain. But luckily, I have an easier way to look at them, which I like to compare to countries and flags to explain how that works. Because I can give you the name of a country, like the Netherlands or UK, but I can also give you the flag. And in some situations, the name of a country tells you a lot, but in some situations that is ugly or inconvenient, and the flag is the same identifier for the country. So if I want to support a sports team, I can just paint the flag on my face, and you'll know which country I'm talking about. And it's the same with these monads. I can give you the very complicated description in functional programming, but actually they are the same as things we know, which is algebra. And algebra is just times and plus, really. And so what I'm actually studying when I say I'm studying monads is that I'm studying times and plus and how they interact, which is way better. So that's what I'm going to focus on today, just explaining things about times and plus. And then the last one, distributive laws. That sounds scary, but are really something that you know. Here at the top, I've written 4 times 3 plus 2 is 4 times 3 plus 4 times 2. That is a law about times and plus that we all know and we learn in school. And this is a distributive law. This tells you how times and plus interact. And that is what I'm studying, really, how structures like times and plus interact with each other.
Brilliant, that's fantastic. I love it when people explain things using Lego bricks and things like flags. We can all understand, and it's great because monads, they are it's such a complicated and kind of abstract concept to get your head around. So I'm really glad we have someone like you who's going to explore with us a bit further. But as you say, you're going to concentrate on algebra, which is times and plus. And I guess it's quite unusual because certainly I'm guilty of thinking that computer science is all about programming, but actually you don't do programming. That's right. You do.
No. I don't program at all. I know a little bit about functional programming, but in my day-to-day research, I don't use it at all. All I do is writing algebra on whiteboards, and I use my computer to type papers, but I don't use it for anything else really.
That's really great, and it's really interesting. And perhaps towards the end of this Q&A, in about half an hour or so, we'll maybe ask you a bit more about what your day-to-day is like, and if you've got any tips for people who want to pursue a similar path to you. But for now, I'd like to get a bit more into the nitty-gritty. So one of the things that you're doing is writing mathematical proofs. So could you tell us what exactly is a mathematical proof, and how might you go about approaching doing one?
Yes, of course. A mathematical proof is really anything that is about a mathematical statement that convinces people that it's true. Now, of course, it's very easy to convince your friends because they like you and they say, well, yeah, I believe you. But in a mathematical proof, you have to consider sort of the most critical person of your work, and you have to convince them. And I can illustrate that with a theorem about lines, which I'd like to draw.
I'm really glad you've got the whiteboard. This is great.
Yeah, I know. It's great. So when I draw two lines that intersect, then it's a mathematical theorem that this angle, which I can call A, is the same as this angle, which I can call B. But there's one way I can show it to you is I can measure them and show you that they're the same. And then I can draw two different intersecting lines, maybe that have a smaller angle, and then again these two are the same. And I can show you lots of examples, and then maybe you'll believe me. But that's not a proof. Because if you're really skeptic, then you say, well, what about these two, and these two, and these two?
I've done it for all of them, yeah.
So instead, what I do when I do a mathematical proof is I say, well, notice this angle here, C. If I look at the sum of A and C, I see that they're forming this line. So I can write that. I can say A plus, should that be bigger?
Yeah, go a little bit bigger for us, thanks.
A plus C is 180.
Yeah.
And then when I look at this entire angle, I see that C and B also add up to a straight line. It's that one.
Yeah.
So I also have B plus C is 180. Now if I subtract C from both sides, then I have here 180 minus C, and here also 180 minus C. So I have that A is equal to 180 minus C, and B is equal to 180 minus C.
Yeah.
And therefore they have to be the same, because
yeah.
they're equal to the same thing. And what I've done here is I've used the property that we all agree on of the equal sign to convince you that these two are equal. And that is typically what you do in a mathematical proof. You look at the situation, then you state some facts, like these two add up to 180, and then you use logical deductions to get to a statement that you want to prove. And that is what I would describe as a mathematical proof.
Thank Thank you. That's a really nice explanation, and also it's also elegant when you lay it out like that. And yeah, that's a really nice way of explaining it. So I just want to say, we move on, that we are live. So if you do have any questions for Maaike, then just pop them in the chat box, and we will put them to her. But I also want to give her a chance to talk to us about a particular mathematical proof that she's been working on for her PhD, or DPhil as they're called here in Oxford. Although I should also say Maaike is joining us all the way from Switzerland, which is really great. So yeah, do put questions into the box, but otherwise, Maaike, do you want to tell us about your turning algebra upside down?
Yes, I'd love to. Well, let me get rid of these.
Yeah, we'll clear the board. I just have whiteboard envy. I'd quite like one of those myself.
Yeah, you can just buy them online, really.
Have this big delivered package.
So in here, I've had a plus and a times. Mm-hmm. And this is the rule we all know and be comfortable with. But then I ask myself, well, why is it that way round? Why can't you have 4 plus 3 times 2 is 4 plus 3 times 4 plus 2? This may seem like a ridiculous question, because well, you can just calculate what it is. Let's do that. So this is equal to 4 plus 6, which is 10. And this is equal to 7 times 6, which is 42. And well, obviously, 10 is not equal to 42, so going back, those two are not equal.
Yeah.
However, sometimes there are really ridiculous equations that, if you look at them the right way, they make sense. For instance, the equation 9 plus 5 is 2. That's absolutely ridiculous, right? It's just
that doesn't make sense. Yeah.
Except when I tell you that it's about a clock.
Ah. Yeah. 9 at 5 hours.
9 o'clock plus 5 hours is 2 o'clock.
Mm-hmm.
So even though 9 plus 5 is 14, which is not the same as 2, seen in the right number system, it makes sense.
Different context, yeah.
So my question of my DPhil really was, even though this, if I switch plus and times, it doesn't make sense in the normal numbers, is there a different system where it might make sense?
Yeah, makes sense.
And the answer is no. It doesn't. Even though you can do crazy things in other systems, you can never switch those two.
Okay.
And I can explain to you why, if you're interested.
Yeah, do go ahead, and we'll chip in if we have questions.
Yeah. Now I'm going to move over to this side of the board a bit.
Yeah, that's great. Thanks.
So what I'm doing when I'm analyzing the systems is that I'm looking at the properties of plus and times. And I'm sort of abstracting away from the specific numbers, because I want to say something about all systems. And I can't possibly study them all, because just like the proof with the lines, I can't possibly measure every line intersection. So I have to go a little bit more abstract.
Okay.
And properties that are important for plus are that it doesn't matter which way around you write the numbers. So we have 4 plus 3 is the same as 3 plus 4. Yeah. And that is a property called commutativity. That's the expensive word for that.
I'm very impressed you're writing that out.
And so we're going to use it later on.
That's really helpful.
And so that is one property. Another one is that I can place brackets however I want. So if I have 1 plus 2 plus 3, and I place the brackets this way, that is the same as 1 plus 2 plus 3, but the brackets this way around. That is also a very important property that we use in numbers all the time. We don't even write the brackets usually. That is called associativity.
Need a spelling degree as well.
Yeah. And then there's one more property that I want to point out, and that is the number 0. That was actually discovered quite late compared to other numbers, but it's really important in how we use numbers, because it has this property that if I add it to any number, then I just get that number back. So 0 plus 4 is 4. And also the other way around. 4 plus 0 is 4. Now, of course, because we already knew that the order doesn't matter, this equation is redundant. But I'm also studying systems where this does not hold, so then you kind of need both.
Yeah.
Now, if I look at these 3, this is called unit. That's the name for it, unit.
Unit, okay.
Then all of these 3 rules also hold for times.
Oh, okay.
So, because if I replace the plus with the times, then it still works.
Yeah.
3 times 4 is 4 times 3. Bracketing doesn't matter in times. And times also has a unit. And I'll write that one out underneath for you. Because it's a different number, it's 1. 1 times 4 is 4. And also the other way around.
Yeah.
So when you look at these properties, then what is the difference between plus and times? Because they all have these properties. There's one very last property that plus has, but times has not. And that is an inverse. Can you see the bottom of... I'll tilt this a bit so you can see the bottom.
Yeah, if you tilt it like that, that's great.
So then an inverse is that for any number, I can find another number, it's negative, so that it adds to the unit, to 0. So if I have the number -4 and I add it to 4, then I get 0.
Ah, yeah, okay.
And for any number, I can do this. But, and that is called inverse, so I'll spell that out as well. Inverse. But times does not have this. Now you can say, well, wait a minute, times has the equation that 4 times 1/4 is 1. So why do I say that times doesn't have this equation? It clearly does, except for 0. So I said here I can replace the 4 with any other number, and it works. But if I replace the 4 with a 0 here, I want to have 0 times something equals 1. Well, there is no.
Yeah.
There's no number that satisfies this.
Mm-hmm.
And that is a crucial difference between times and plus. And eventually that leads to why this equation from the beginning works one way around and not the other. And I can even show you why.
Show us why. I should. We do have some questions in as well, but as long as you're happy and don't need to rush off anywhere, then it would be great to hear a bit more, because that's super interesting.
It's quite quick.
Go for it.
I do need a bit more space though, so I'm going to create that here.
Well, these videos will be left online afterwards. So if anybody wants to go and flick back and look at what you wrote, then you can easily do that.
It's all hinging on this equation. For any x in the normal number system, we have that x times 0 is 0. I'm so sorry.
You spotted it before I did. It's fine.
Now, because I'm changing the roles of plus and times, in this new system, if I want this other equation to hold, where the roles are turned upside down, then I can prove, which I won't show you, that we will have x plus 1 equals 1. And you see that the times is replaced with a plus, and the unit for plus is replaced with the unit for times. Mm-hmm. So it kind of makes sense that if you have this equation in the normal system, then you will have this in the new system where they're turned upside down.
Yeah.
But because plus has an inverse, I can use that inverse. I can say x plus 1 plus minus 1, the inverse of 1, is equal to 1 plus minus 1. Mm-hmm. And if you simplify that, then the minus 1 and the 1 will cancel, so you will get x is equal to 0. And this is for all numbers x. So I've just proven that if you switch the roles of times and plus, then every single number is equal to 0. Well, that's a bit boring. You can't really do much.
Yeah.
In such a system, and that's what mathematicians call the inconsistent system. It's a valid system. It's just very boring, and it's not something you want to work with.
Yeah, understandable.
And that's why you can't change the roles of plus and times. And you can see that in this equation, in the original one, I can't do the same trick because 0 does not have an inverse. Mm-hmm. And that's why.
I feel it would be patronizing to clap, but it's really great to watch you lay out like that. So thank you so much. I don't think I've ever watched a proof take place before. So thank you so much. And it's really neat. I kind of want to move on to the questions, if that's okay.
Yeah, exciting.
People are obviously very interested. I'm not quite sure which one to start with. Somebody whose name is probably not really 447X Pro asks, stepping back a little bit, talking about agreeing on the definition of equality, are there any cases when equals is not bijective? aka, is it ever true that A equals B, but B doesn't equal A?
No. So equals is a very special relation between two numbers, and it is defined as having these properties. Mm-hmm. So if you go really into logic and how these rules work, then the concept of equals is defined by its properties rather than it's magically appearing and then studying its properties. It's really defined as having that commutativity property.
Makes sense. I like it. A very clear, definite answer is no. But thank you for your question. It's really great to have them in. And Martin asks, how would you start working on a mathematical proof? Is there a clear place where you'd begin in each case, or does it vary depending on the particular question?
It varies a lot, and it's kind of one of the hardest parts of a proof. Is a good way to start is to look at the properties of your problem. In the case of the lines, all we really had were two straight lines that we knew for certain were straight. So you can see, can I use this in any way? And with the numbers, the most of the creativity is in the start. You just try some things, and sometimes you get stuck, so you try something else. And after you've done a lot of proofs, you develop an intuition of what works and what doesn't in certain ways, and in certain cases. but it's really the start is the hardest.
Tricky, a bit of trial and error, I guess.
Yeah,
But
a lot of trial and error. I've written a lot of whiteboards like this with long deductions that just didn't lead anywhere.
I can imagine. We were having a chat there the other day, weren't we? And you were talking about a proof where you were surprised halfway through. Could you just tell us a little bit about that?
Oh yeah, it was such a lovely feeling. When you've studied a problem long enough, sometimes you develop a proof plan. You kind of see, if I apply this technique and then that technique, then I will get to the end. I often see it sort of as a long road. I want to get home, and I see my home, and I see that the road is straight, and it's going to take me a while to get there, but I just need to step one foot in front of the other, and I'll get there. And where walking is applying rules of logic, and I'll get there. And I thought I had such a situation. So I was walking down this road, I was applying my rules, and suddenly, out of nowhere, the road turned left. It's the only logical rule I could apply was not the one I thought I could apply. And it took me in a completely different direction, and that was amazing. And then you get quite scared and like, ooh, what if this road doesn't take me home? But I kept on applying the most obvious logic that I could find to apply to the next step. And eventually it brought me home, and it took a whole detour, and it was just absolutely amazing.
That's fantastic. I really love that idea of it being your path towards home, and you're finding your way. That's a really nice way of looking at it. But yeah, it must be really exciting for you as well for something like that to happen, and you go off in interesting directions.
Yeah, it's when I finished it, I just thought, oh, but I need to backtrack. I need to see what happened there.
And then have a little celebration afterwards, because
yeah. And I must add that most of the proofs don't work in this linear thing. It's more often that you start from both the beginning and the end. And it's also often a good point to start with, okay, I want to have this conclusion. Which logical steps can let me reach that conclusion, and then sort of work backwards. That's a technique you use as well a lot.
Yeah, that makes sense. Brilliant. So we've just got a few more minutes. I'm just going to backtrack through some of the questions. We've had some really nice comments of people saying that they have enjoyed your presentation, and it was a really nice, clear explanation. So thank you so much to both the commenter and to you. Let me see. This is a little bit of a different question. I'm not quite sure whether you'll be able to comment, but Kashif asks, do you think it's possible for software engineers, or more generally people who don't research full time, to contribute to this kind of research?
Yeah, absolutely. Basically, research is accessible to anyone, whether you're at a university or not. If you want to start, I would say get hold of papers. Most of them are available free online on archives. That's spelled arxiv. You have to be a bit careful because that is non-peer reviewed, so there could be mistakes in the material presented there. Well, there could always be mistakes, but peer review is kind of to weed out the ridiculous science from the real science, and people just put all of their papers on archive. And so if you kind of be careful about what you like Wikipedia, there can be nonsense on Wikipedia, but you have to develop a sort of intuition of what is nonsense and what you can use.
Yeah.
So if you don't have access to journals with research, then you can always go on archive and still get the information. Or you can email the people that you want their papers from directly.
Yeah.
And you can just start scribbling yourself on a whiteboard or some paper. You can read loads of background information and then just start doing the research yourself. And if you think you have something interesting, you can always write to anyone to see if you can get it published. It's absolutely accessible to anyone, really.
Brilliant. That's really nice to hear, and a really good tip about archive. I'd recommend that as well. And I think often people think that researchers and scientists are very out of reach, but it's not the case at all. I'm sure there's lots of people who would really love to hear from you if you were interested in their work. So yeah, brilliant. Thank you for that. Gimika asks, what would be your ideal goal to reach with this research? Do you have an ultimate dream for your work?
Yeah, I kind of do. So earlier I mentioned these monads, and that by studying these algebraic properties, I learn a bit about the monads and how they fit together. Ultimately, I would like for sort of every monad, every two monads you can give me, to be able to say, do they fit together or not? And if they do, how? So it's kind of all the different ways, times and plus and other algebraic things, I want to know how they interact and how they cannot interact. This is just one example. And yeah, that's my goal, to find how all the Lego pieces fit together, really.
Excellent. That's perfect. It's really nice to have a clear aim in mind like that. And I guess, how far are you into your PhD at the moment?
I'm writing up.
You're writing up.
In September.
So this is maybe something for your research into the future. But
yeah.
Fantastic. And sorry if I've missed anyone. It's been really great to have in so many questions. I didn't introduce myself at the start. I'm a biologist, and I'm unfamiliar with some of the terms in this question, so I'm not quite sure, but I'm going to read it to you, and it might not be your area, but Joel Beckles asks, what are your views on some of the misrepresentations of equalities, like with Ramanujan summation? Am I saying that right?
Yeah.
He sounds like he knows what he's talking about.
I must say I haven't looked into that much, so I can't really comment. I'm sorry.
No, that's a perfectly acceptable answer. Normally I try and think, is it relevant? But because it was a term I wasn't so familiar with, but anyway, we'll
It's definitely about logic and equality, but that field is so big. Yeah, I'm only studying a tiny subfield of it, and yeah, I don't feel really qualified to comment on that. I'm sorry.
It's the same with any PhD, honestly. It's you get to know your subject so well. Because she says, thank you very much for your answer to his question. Brilliant. So I think just before we finish up then, I said back at the start that we might just hear a little bit about sort of what a day in your life is like. Obviously, that'll be a bit different at the moment in lockdown. As a researcher, maybe if you have any tips for people who are looking to pursue a career in this field, any pearls of wisdom?
Basically, be enthusiastic. There are many scientists studying a lot of different fields, and find your passion and go with that. That's how I got into Oxford. I was really enthusiastic about something, and I wanted to explore that, and they gave me a chance, and it wasn't actually this. Halfway through studying that, I stumbled into a problem that was related to this, and then I got that was so much more cooler even than I could have imagined the other thing being, that I just ran off in this direction.
Yeah. Things can sometimes work out like that with research. You stumble upon something and go down that trajectory. But
yeah, really, if you find anything in life where you go, that's interesting, go search for information, and you might find out that it's not known what the answer is, and then you might be the person answering it.
Absolutely, which is super exciting and brilliant. That's really nice to hear. Well, we've just gone over our half an hour. I think we could spend a lot longer chatting, but unless there was anything else you would like to share with us, you're more than welcome to. We will probably start to wrap up. We've had lots of people saying thank you for the talk and saying hello, so hello back to you.
Yeah, I know a lot of my friends are watching. I thought in the advertisement for this talk we talked about emojis, so maybe I should mention those.
You're right. I was thinking we'd come on to them earlier when you were talking about the different operators. Yeah, that would be great, just to finish up on a fun note.
People who tuned in to hear about that, I don't want to disappoint anyone.
You're completely right. Thanks for reminding me.
So I'm going back to this side of the board where I said I study all these properties, these abstract properties, and because I'm so used to how times and plus behave in the numbers that, actually I can go back to this slide. An equation like this, x plus 1 is equal to 1, it can be so confusing. You should think, well, that can't be right, but in the system that I'm working, it is right. And then to combat that problem of confusing myself, I sometimes replace this with either a heart or a smiley, just to know that it is not the normal plus. So because the equation x heart 1 is equal to 1 doesn't go against your intuition as much, because there's no intuition about how heart behaves. So really, when you have a screen capture of a whiteboard I'm working on, sometimes there'll be pluses and times, but quite often it's filled with hearts and smileys just to keep confusion away.
So someone looking over your shoulder must wonder what's going on, but it's not just for fun. Getting rid of those misconceptions.
It has a goal, just to keep myself from making mistakes.
That's great. Yeah, your pages must look very fun. I like that. And that's a brilliant way to finish off. So thank you so much for talking to us this afternoon, Maaike. As I say, we don't sort of get to hear about this kind of research, and it's super interesting, and it comprises a lot of what's going on in different departments, well, everywhere really. So thank you so much. And as I said back at the start, we're holding these every week, and next week we're going off in an entirely different direction, over to the Institute of Biomedical Engineering, where we're going to be hearing all about needleless vaccines with Johanna Hettinger. And that is going to be, I was just checking at the time, that's going to be at 4:30 next Tuesday, which is the 7th of July. So if you're joining us for the first time and you've enjoyed this, then please do join us again for another one. Ask any questions that you want to, and we look forward to seeing you then. So for now, I'll say bye from me, and bye to Maaike.
Yeah, goodbye, and thanks for talking.
Brilliant. And thank you so much again for all your questions, because yeah, it wouldn't be the same if we didn't have the interaction. So that's great. We'll see you next week. Bye-bye.